When most people think about the planet, they think of it as it is. But when you study geology, you realize that the early Earth was not at all like it is at the present time. What gets geologists up in the morning is the possibility of determining how the Earth got to be as it is now. The appearance of oxygen in the atmosphere is extremely pivotal in terms of how the planet developed, in particular in relation to life. Once oxygen built up to the point that there was an ozone layer, then life could come out of the sea and come onto land because it was protected by the shield from ultraviolet rays from the sun, which are deadly, which can destroy the body of the organism. Oxygen is one of the things that renders our planet pretty unique in the solar system and possibly in the universe.
I've often wished that I had a time machine to go back and collect an ancient bit of atmosphere, but we can't. All we can do is collect rocks that were formed under that atmosphere. So we go into ancient mountain ranges and we collect rocks and we tease them apart to try to understand processes that tell us something about that ancient atmosphere.
The Huronian Supergroup is a thick accumulation of mainly sedimentary rock. At its thickest point, it is about 6 to 7 miles. It's located at the south edge of the Canadian Shield. By radiometric dating, we know it's between about 2.47 billion years and about 2.2 billion years. The Huronian group is particularly exciting and interesting because, by chance, these rocks were laid down at a period when the atmosphere underwent a transition from containing, we think, no free oxygen to containing at least some free oxygen. In order to investigate the atmosphere, we look at minerals in the rocks that react to the presence of oxygen.
While we were in the field, we looked at various levels of the Huronian stratigraphy. What you got here is sandier layers and then muddier layers here. And the mud is almost purple in color, indicating a high iron content. But even the sands are also oxidized. They have this pinkish or reddish color due to the hematite.
So we think it's very shallow marine, very shallow amount of water above the sediment when it was laid down, therefore a very close contact with the atmosphere. And the atmosphere at this time may have contained at least some oxygen, and so we get this red coloration. That red color is a very good clue because it tells us that there was this reaction with oxygen. So it's a very simple kind of test, but it does give us at least a first order idea as to whether there was free oxygen or whether there wasn't.
This will be sample KY03-5. The rocks that we collected from various levels in the Huronian stratigraphy would bring back to the laboratory. We'll chip them with hammers, we'll crush them in grinders, and eventually the powders will extract with various chemicals to pull out sulfur, because it's sulfur that's telling us something, we believe, about the ancient atmosphere. Most of the sulfur in the atmosphere comes from volcanic explosions, and that sends a gas called sulfur dioxide high into the stratosphere. In the presence of UV radiation, sulfur dioxide will interact with ozone to form a certain compound of sulfur that gives us a signature that we can read in the rocks. However, in the early Earth, because there was no oxygen, there was no ozone, and without the ozone, there's no reaction and there's no signature in the rocks. And it's those ancient rocks that we're now bringing back to the laboratory to study that ancient atmosphere.
To better understand what the sulfur signature meant, we went out and decided to analyze a variety of samples from Australia, Africa, Greenland, North America, South America, and Asia. And the conclusions are the change from a large signature to a much smaller signature at about 2.5, 2.45 billion years ago is a result of a large change in atmospheric oxygen content from levels 100,000 times less than present to levels within about 100 times of present levels.
The most exciting thing to me about this research is that it quantifies amounts of oxygen in the atmosphere. Before, we just had this qualitative sense of, well, it was low here, it must have risen here. But the sulfur signatures that we're seeing allow us to actually get at numbers. The study of the ancient atmosphere does tell us something about the evolution of life on this planet. We have an intense desire to know where we came from. And that knowledge drives us to understand the earliest biology, the earliest atmosphere, what is the origin of life. And those are the driving forces that send us into the field to study these truly ancient rocks.